Okay, let's get going. So today we're going to continue our discussions. We were talking about Faraday's law and was leading us into discussing generators, so how most of the electricity that we use is made, and continue talking about that stuff. So we're going to start a little bit now talking about alternating currents. So far we've dealt with direct currents primarily. And so an alternating current is a current that switches back and forth. So basically you can think about it as kind of like being like a battery that sort of, it's positive and negative switches back and forth. And so primarily most of the stuff that we deal with at our homes, and when you plug stuff in, it's AC current. So our homes primarily use AC current. And so it's important to understand some basics of that. So again, the current basically switches direction over and over. And we sort of had a few examples that dealt with things that were AC. And so the frequency that it switches is like 60 hertz at home. And so that means it's switching back and forth 60 times per second. And so why? Well, we're going to talk today about the two main reasons. So first of all, it's easy to generate, or sort of natural to generate, alternating current, which we'll try to talk about. And then we'll talk about something called a transformer, which is maybe more important reason why AC is primarily used. And so where we left off, we were talking about Faraday's law, and we had a picture of a generator. And literally what that is it's just a loop inside of a magnetic field that's rotating. And so here we have this sort of carryover picture from last time of this. And so if we remember from last time, our magnetic flux is something like this. So BA cosine of theta. And so in this picture here, this thing is rotating. And so we set it up so that our loop, say, starts here and starts rotating from that point there. And so at that point there, its magnetic flux is the maximum, just B times A. And so if you were to draw the picture, our magnetic field was kind of pointing this way. And then our area vector would look something kind of like this here at that sort of initial point. And again, so this is like, it's like a three-dimensional loop, or like a sheet of a loop. And what we're doing is we're sort of looking the top point down. So the magnetic field is coming through this loop. And just like last time, as we do this, as the flux through this loop changes, we're going to induce EMF, which will make a current. And so again, this is how you generate this electricity in the first place. And so what we're going to claim is then that our flux can be written this way here. So BA cosine omega t. And so we talked a little bit about this omega and the t. We'll talk about it a little bit again as we go on. And so if you look at this picture here, this angle is changing. So what's in here is going to be an angle, right? An angle measured in radians. And our picture here, as this thing moves from the point we looked at, it moves some angle, and that angle is going to be omega times time. And again, omega is going to be in units of radians per second. Time would be second. And so this turns out to be radians there. And like I said last time, I think this is something that we typically haven't dealt with too much. So we're going to spend a little bit more time just sort of trying to get a better working knowledge of that idea, I think. But once you accept that, which we'll keep talking about it, then by Faraday's law, we can go through here and then just take the derivative of that flux. And then one thing is, so basically, typically what happens is for one loop, that equation is BA times cosine of omega t. But typically, when you do this, to sort of maximize what's going on, you'll put a whole bunch of loops in there. Okay, when you see a generator or something like that, there's usually a whole bunch of loops. And so that N is just what we put in there. So sort of the flux for one of them is BA cosine, and the flux for 100 or whatever it may be would be N BA cosine. And so when I take this derivative, it's not a very tough derivative, but we get this here. So our EMF works out to be here a sine function. So our the voltage through this loop, it turns out to be something that naturally alternates. Okay, that sine function is going to be positive and negative at different parts as it goes on. And so we come out of this then with an EMF that's going to naturally go from positive to negative and back and forth. And so it's naturally going to be what we're talking about as an alternating current. And just a little bit, I kind of just want to sort of look at this, make like maybe a little table here. So we'll do time versus the actual flux. So our flux here, we wrote as NBA, again, cosine. Now I'm just going to make an example, I'll make sort of a simple one. So let's say we have this thing is rotating with a frequency of 1/2 revolutions per second. Okay, so this thing's rotating 1/2 revolutions per second, which means it takes 2 seconds to go all the way around. All right? And so if we set that up, our omega, the angular frequency, which again is just the frequency in different units, would be 2 pi and then times 1/2 revolutions per second. So the omega equation is 2 pi times the frequency. It's literally just converting this into radians. And so your omega, in this case, for the example I did, would be pi radians per second. And so over here, then for the particular example I made there, you would put in our equation cosine of pi times time. Now, of course, depending on how fast you want this thing revolving, that would be changing, but just to kind of explore what this sort of means to us, that's a nice example to use. And so what we can do then is just sort of plug in different times. So like at time 0, you put a 0 in there, and you get just the maximum flux. Okay, and hopefully that when omega t is 0, the magnetic field lines are sort of primarily pointing through there, and so that would be the time equals to 0. So this guy would be aligned right here at that time equals to 0, so you'd have the maximum flux coming through. And so now if we start rotating this, we'll do time of 1/2 of a second. And so for this flux then, we get NBA, and then here would be cosine of pi times 1/2, or cosine of pi over 2, which gives us 0. So after a 1/2 a second, pi over 2, so that's like 90 degrees. All right, so this thing then has rotated from this point, and so now it would be this way here. So it's completely parallel to the B field lines, so there's no magnetic field going through there, so there's no magnetic flux. And we can just sort of keep going. So at 1 second, I would then have NBA cosine of pi, which gives me negative NBA. All right, so this thing now is switched all the way around, so it's kind of flipped, and now it would be oriented this way here. Again, this thing is turning around. And so now it's oriented this way, and so our area vector would still be pointing this way. And so now the area vector and the magnetic field are opposite, and so that's why you get the negative sign. So what was before positive flux would now be negative flux. And then we can just keep going from here. So the next time would be 3/2 of a second. And so you'd get NBA cosine of 3 pi over 2, which is again 0. And so that would be that thing flipping back to where it's 0. And then finally, after the time of 2 seconds, you get NBA cosine of 2 pi, which would give us that maximum. So it's right back again to where it started from. Okay? So questions on that? Like I said, I think typically this omega and kind of sine functions, people haven't seen too much of this, and so it can be a little bit confusing. And of course, I just picked this frequency just to be kind of an illustrative one. You know, in our daily lives, this frequency is more, that starting frequency would be 60 revolutions per second. And so here's like a picture. Your book has diagrams of this, of a real simple kind of generator idea. And so again, you're rotating this loop in some kind of external magnetic field. And again, the EMF you get, the voltage you get out of that is going to be going like this. So it's positive, negative, positive, negative. So the EMF was, again, the derivative of that flux we were just talking about. And so this is where hopefully you can see that it's just kind of natural or simpler maybe to create alternating current. And so that's one of the big pluses. And then here's just the relationship between how we set this up. So again, our flux was this NBA cosine omega t, and then the EMF, that should be kind of a squirrely E there. So you can see that relationship there. And basically it's just the same relationship between a sine and a cosine. So when you can just sort of see that, like, for the EMF, you get this maximum of the EMF when the slope over here is sort of its steepest, right? And then when the slope over here is 0, you get 0 EMF. And so these are just related again, because this is the derivative of this function over here. Okay, so let's look at this just kind of physically to try to just relate this back to what we were thinking with Lenz's law. And so here's, again, sort of a top-down view of a loop in a magnetic field. So the green lines of the magnetic field, our loop is, rotating with the angular velocity as shown. So at this moment, okay, so you're looking at this loop, and so basically it could be that the current is coming out here, kind of going down here and going in through here, or the current could be coming out from the yellow, going up through the loop and then back over to here. So it's, again, with all these pictures with magnetism, it can be tricky. But in this picture here, which case is the current going in, knowing what we know about Lenz's law? So let's try this and see what we think. Okay, so let's go ahead and call time here. So I'm going to look at this. So I think I agree with the majority. Majority is saying A. And so let's look here. Again, what can be really tricky with these things is visualizing this. So let's imagine that, here's my head, here's my eye, and so I'm watching from this viewpoint over here. Okay, so you're looking at this loop. And so this, again, if we do our before and after pictures. So maybe there's two lines pointing out at you at 1 second, and then just sort of the next little second as it moves, there should be less lines poking through there. So it's heading towards that place where it's going to be flat soon. So again, sort of looking this way, if you think about it before and after, as it's turning this way, it's going to be having less lines in it, which means that what I want to do is I want to have the magnetic field, I want it to look like before, and so I want to sort of reinforce the magnetic field that's there, which would have it coming out of the gray side and in on the yellow side. Again, sort of what the majority had. Questions on that one? I know straight up just visualizing this is pretty crazy, but it's hard to draw this picture. Yeah. Sure. So I'm sort of looking at the loop here. So there's like a loop right here, right? And so as I look at it, the B field's pointing to me, all right? And so as it moves, there'll be less B field going through. All right, so what nature wants to do is it wants to keep the magnetic flux through the same, and so it wants to make a magnetic field pointing at me, which would be, in sort of my picture here, a counterclockwise picture, which in that loop means it's sort of coming out at the top, sort of going down the side and coming in for the bottom part. Does that make sense, Ben? Okay. Okay, and so now, just to see, to sort of hit this home, and we want to try to connect this to what we were doing from before. Let's look at now later on. So here you had the Yeah, so here, if you look at this, so these pictures are tricky to visualize. And so right here, you've got the yellow down here and the gray down here. And so what's going to happen is sort of a half a revolution later, they'll switch, and you'll have the yellow here and the gray down here. Okay, so it's sort of a whole half revolution switched. And I want us to think about the same picture. Okay, so you're looking at the same loop as you were this one, just it's sort of a half revolution to the other side. So now, which way will this be going? Okay, so think about this with your neighbors and see what you think. Okay, and so I think I agree with the majority again, which is good. So it's actually, it's a little bit tricky. It's actually, if you just disregard the colors, it's the exact same picture, right? That loop is again, it's right here. So if it's in front of me, the loop is turning, so there's less magnetic field coming through there. All right, and so you want to sort of make that magnetic field stronger, all right, by having a counterclockwise. So again, it's, if you look at sort of, it's coming in out at the top, down the side, and in at the bottom. But because the loop has changed by a half, what that means is the current, according to the loop, is going in a different direction. Okay, so because because the loop has rotated, and so what I'm trying to get you to see here is that just by using our Lenz's law, we can see this nature of the alternating current. Okay, so it's sort of going one way in the first case, and it's going the other way in the second case. All right, but again, that can be tricky to visualize. Questions on that? So it's nothing, necessarily new. It's just we're sort of applying it to a different situation. But this really just is applications of Lenz's laws and Faraday's law all over again. Okay. Okay, great. So here's one. I thought we'd try this. We don't a lot of times do numerical exercises, but let's take a few minutes here. So this is like an old test question for this type of material. So a generator exists as below. So it's, again, really hard to draw these things, but you've got that similar sort of shaped loop, and it's rotating with some angular velocity. It's got a total of 10 turns. It's got a certain area of 0.01 meters squared, and the magnetic field is 0.1 Tesla, and it's set up in a circuit with a light bulb. So it's kind of like that one we had in class the other day. So you're lighting up a light bulb with this. And so what we're saying is the light bulb will burn out if the current through it is bigger than 0.5 amps. So what is the maximum rate at which the coil can spin so that the current does not exceed this limit? So discuss this with your neighbors and see what you think. Okay. So hopefully you've had a chance to think about this one a little bit. Again, I just wanted to kind of, it's always good to just at least try starting one of these things. And if you look here at the answers we got, so the two big ones are A and C. So I agree with, or I sort of see where both of those come from. So the actual answer is, in fact, C. Okay, so let's go through and talk about this. So first, what's going on here is you've got V equals IR. Okay, so you look at this light bulb and you say, okay, well, the light bulb, the maximum current, we're saying before it burns out, is 0.5 amps, and its resistance is 200. And so when I go through and do that, I get that what we're saying is that the light bulb can have a maximum of 100 volts through it. Okay? And so then what you want to use is you want to say, okay, well, we have this equation for our EMF in a case like this, and our equation was this NBA omega. Now, the thing is it's times cosine, right? But that NBA omega, that's the maximum that this value can be. So it seems like a lot of people got that idea. So that's the good thing. So sort of okay, so E max is NBA omega. And so that's the maximum that let me write this. I'm sorry, I'm having trouble writing this so it looks legible. Omega. And so what we want to do is we want to equal that to 100 volts. And so I think if you got 1, okay, if you solve for omega, all right, that answer there, you get omega equals 1 times 10 to the 4 revolutions per second. So what did the person who wrote this one do that's really jerky is that they wrote the answers in frequency F, okay? So in frequency F, which, you know, the book problems tend to do that. They tend to want you to get really good at converting that back and forth. And so if you take omega divided by 2 pi, all right, then you come out with this answer for frequency in revolutions per second of the 1.6 times 10 to the 3rd revolutions per second. So I kind of wanted to do that again, just to sort of hit this thing home, because I think a lot of us don't, in general, have a lot of familiarity with that. Questions on this one here, anybody? Okay. And so then just to kind of wrap up this section on generators, so again, here's our EMF equation. And so what will often sometimes happen, so there's actually a problem on our discussion sheet tomorrow, having you kind of walk through this. So this would be the EMF. Now, if you want to find the current, right, that's typically sort of the next step in a lot of these problems, and it's usually just a matter of dividing by the resistance. So you divide it by that R, right? And then now we've got this current in this loop. Anytime there's a current going through something in a magnetic field, you can have a torque. Okay, so we talked about this. This is one of those things where we sort of showed this equation briefly. I think there was like 1 or 2 book problems on it. But there's a torque on this loop caused by the magnetic field. And so it looks like this. It's the N times the area times the B field times the particular current that's in there. And so what you can do is just plug in your value for the current. Okay, and this is just sort of trying to set you up a little bit for this problem and discussion tomorrow. And so this is the torque. But the main idea is, like with a lot of these kind of problems, is that if you're sitting there rotating this, say, to make this electricity, to generate this electricity, there's this torque that's constantly trying to spin the loop down. Okay, and so you have to supply an external torque to keep it spinning at this constant omega, right? So you don't just get sort of free energy. You've got to be putting this torque in, so you've got to be driving this thing here. And so there's something always, in this case, going against you. Okay? But again, we'll sort of deal more with that a little bit on your discussion sheet tomorrow. So I just wanted to kind of get ahead of that a little bit. AC is power transmission. Okay? So what happens is generally your power is generated at one point and you want to move it to some other point. Okay, so the second reason the AC current is preferred is this thing we're going to look at called transformers. And so basically we're going to talk a lot about power. And if you remember, power delivered, you can write it in kind of different ways, but power delivered by something is I times V. So it's the voltage times the current. And so what you can do is when you're delivering the power, you can sort of take the same energy, power is energy per time, and you can either have it really high current with lower voltage or higher voltage and lower current. All right, and what happens is that our house, we prefer low voltages, right, because of this, right? Now, when we transfer the power over a power line, we prefer high voltages and low current because that loses less of the power. And so you sort of have this problem, and transformers are a solution to this problem. All right, and so it's another application of Faraday's law. So it's something that we totally use Faraday's law for. Here's my dated picture of a transformer. And so this is a key, I would say a key to our modern electrical systems. So starting with 120 volts, you can produce arbitrarily small voltages or large voltages. And it's like nearly 100% efficient. And so you can basically, what transformers do is they take extremely high voltage a source and then near your house and transform it to 120 volts to use in your house. Where again, if they transferred it at the 120 volts, you would lose a lot of power. And so the way these things kind of work is, here's sort of a picture of this phenomenon called mutual inductance. And so if you have two coils, okay, and so imagine you have an AC generator going through, this is just a solenoid, it's like two solenoids, and so it's pumping current through this thing, and since it's an AC generator, it's constantly changing sort of its positives and negatives, again, 60 times per second. Okay, so switching back and forth, back and forth. So the magnetic flux through here is constantly changing. All right, and so you have this because there's a current here and it's going backwards, and so a solenoid makes a magnetic field, so it's constantly changing its flux back and forth. And this flux goes over here into what we call the secondary coil, and it induces, okay, again, according to Faraday's law, a EMF over here, which you can read as a current or as a voltage. And so that's the idea of a transformer. So you're using this again, idea of Faraday's law. And so here's how typically the pictures will look like. And so you're going to have the primary, which would be here, and the secondary, and you have a piece of iron. And what that iron does is it's just the kind of material that sort of makes sure that it redirects the magnetic field. And so you have this, so here you've got your primary source, and it's going to be an AC, sort of like a generated, something like we just were talking about. And so it's a current going here that's changing back and forth. And so what happens is you create this magnetic flux, okay, changing magnetic flux, and the iron sort of works to sort of redeliver it over here. And so you basically have the same flux over here as you do over there. And by changing the number of these coils, okay, you can change the different voltages you get. And so you can think about it as the voltage of the primary by Faraday's law is basically the number of primary loops times the change in flux. And the voltage of the secondary is the same thing, but with the number of secondary loops. And the idea here is that the flux through this iron, the change in the magnetic flux, okay, we should make sure these are all changes in magnetic flux, is the same. And so you get this relationship that Vs over Vp equals Ns over Np. Okay, and so this is sort of the key equation. So I'll write this over here just so we have this down somewhere. Or maybe not. Yeah, sorry, I won't. There's no chalk. All right, but that's the relationship that we're looking at. So you want to write this down somewhere because we're going to use this for a little bit. Okay, these two relationships are the same. And the thing is the energy, or sort of the power that you're using here will be the same. So by energy conservation, the I times the V at the primary is the same as at the secondary. So basically, you can have a high voltage and a low current, or vice versa, when you switch these things. And so let's try one of these things here. So here's an example of something that might happen like this. So the good news is you're going to France. The bad news is that France, The outlets have 240 volts. And so what you usually will buy, okay, at like the store or something, is a transformer that converts this, which you could also, if you were really into it, try to create your own. And so you remember from physics that you need a transformer. So you wrap 100 turns around the primary. How many turns should you wrap around the secondary if you need 120 volts out to run your hair dryer? So let's talk about this one and see what you think. Okay, so I think that's most everybody, and I do believe I agree with the majority, so that's great. So again, the way you would look at this is our relationship, and so in this case, you're trying to find NS, the number of secondary, and so you can plug it in, and so for us, 100 was the number of loops for the primary, and then the difference in the voltage is 120 and 240, and so you'd want to put 50 in that secondary. Okay, again, the idea here that this resistor is your hair dryer, and you want to get the sort of similar voltages to that. Okay, so let's call time on that one. And then here is another one. So now you're doing the same thing. We're using a 12-volt battery like we might have used a couple weeks ago, okay? And so in this transformer here. And so what is the voltage across the secondary after the battery has been connected for a little bit? So you cool up your battery and you sort of let it do what it does. Maybe take a couple seconds, and then you want to measure the voltage over the secondary at that point. So what's going to happen in that case? Okay, and so I think we've got sort of two big lines of discussion here. So B and D. And so let's look at this here. So I'm going to say 0. So let's think of this. Why did I say 0? Anybody want to tell me why I said 0? Yeah. Because so we said there's no change in the flux. So it's really important here that the whole idea behind this is that voltage has to be AC. It has to be switching. All right? When the voltage is switching, the magnetic flux is constantly changing. If you have just a regular 12-volt battery, what happens is when you plug it in there, it makes a current, which creates a magnetic field, but that magnetic field is static. It's not changing. Okay? And so this, again, is sort of the one of the rationale for why AC is more useful for us is that we can use it with a transformer where DC you can't. It just makes, and so in this case here, it would just do nothing at all. There'd be a zero voltage there. All right. And so here's sort of the explanation of that. So the 12-volt battery is connected to a transformer, but basically there's no, transformers depend on a change in flux, so they only work for alternating currents. And so here we have two of them, so two ideal transformers are connected. A voltage source supplies a 60 hertz sinusoidal voltage with a maximum of 10 volts. What is the maximum current passing through the 100 ohm resistor on our diagram? So let's think about this one here. Okay, so let's go ahead and call time here on this one. So this one's a tougher one, so it's a little bit kind of mixed up. So I'm going to say this is our answer here. And so let's look at this one. So what you've got here is you've got two transformers. So you got a transformer here where this is, again, 5 loops and 10 loops, and then 5 loops and 10 loops. And so if we go back to our equation that we were dealing with, this equation that, again, back over here. So this guy right here, so Vs equals Vp Ns over Np. And so that's our general one that tells you and so you're going to have the voltage of the secondary equals the voltage of the primary times Ns over Np. And so our initial voltage here was said to be 10 volts. So we'd have 10 volts, then Ns over Np would be 10 over 5. So we get 20 volts. And so with this particular gale, so again, we're starting here at 10 volts, and at this in-between point, we've got 20 volts now. And the thing is this one here is just like a mirror image of this one. And so what this is going to do is it's going to step up the voltage, just like that last one, to 40 volts. So the voltage working across this resistor will be 40 volts. And so we just go back to Ohm's law to do V divided by R, and we get 40 volts divided by 100 ohm resistor, and that leads us to 0.4 amps for the current in that particular one right there. So the idea is that when you have two of these, you just work it as one, do the first one, and then basically use that to sort of figure out what the next second one would be. All right, and so here, let's do this one. So the same picture, And so compare the power supplied by the voltage source to the power dissipated in the resistor. Which one of the following statements is correct? So we're delivering a certain amount of power at the beginning point. We want to know is how much power is used up in that resistor. So maybe it's your hairdryer or a light bulb or whatever it might be in the second case. And let's just for kicks, we'll assume that we have an ideal transformer, okay? Okay, and so I agree with the majority here. So the other idea with these things, so again, we're assuming an ideal transformer, but the sort of the picture here is that the power delivered is I times V, and so that's going to be the same on both sides of this transformer. Again, it's one of the positive aspects of the transformer is that it's super efficient. So it's as close to 100% as you can get, and so you don't lose anything, you don't lose energy in this process. Okay. All right, so I think we'll go ahead and stop there. I'll be down here if you have more questions, and we'll see you on Wednesday.